Good afternoon. My name is Donald Trogdon, and my presentation today is on Edgar Dijkstra and his shortest path first algorithm, which is an algorithm for finding the shortest path or lowest cost path for traversing a tree. It's used in networking for routing protocols to find the lowest cost path from the origin vertex to the destination vertex. Edgar Dijkstra was born in the Netherlands. He was a mathematician and computer scientist. He was born on May the 11th, 1930, and died August 6, 2002. His father was a high school chemistry teacher, and his mother was a trained mathematician, although she held no job because she stayed at home with him and his siblings. He had brothers and sisters, and with his father working, his mother would stay home with the kids. But she was a big influence on him, and his father and his mother gave him the foundation for his math and science skills, and he excelled in the natural science classes such as physics and chemistry and even biology in high school. He even scored the highest grade on the exit exams in the natural science and math components of the test. In college, he attended the University of Leiden. He majored in theoretical physics after his parents had to kind of persuade him not to go into law school, which was his first choice, but I think they made the right choice. He graduated in 1956, and then he got his PhD from the University of Amsterdam, and his thesis was on communication with an automatic computer. During college, while he was getting his bachelor's degree, he attended a 3-week computer programming class at the University of Cambridge, where he got his introduction to computer science and computer programming, and this kind of was a big impact on him and influenced him to pursue a career in computer science instead of the natural science and physics that he had been studying in college. He was really interested in computer science and learning programming, and he even said that it was more of a challenge to learn computer programming than it was to learn physics. When he got back home from Cambridge, he was offered a job at the Mathematical Center near his hometown when they found out that he had actually taken this computer programming class at Cambridge. And he really was interested in programming, and he wanted to show people the power of computers, and that's what inspired him to write his shortest path algorithm. And in the 1950s, he would show that a route could be found between any city in the Netherlands. That's what he made the original shortest path algorithm for, was to find the shortest route between two cities in his country. He went on from 1984 to 2000 to be the Centennial Chairperson of Computer Science Department at the University of Texas, and he of course retired in 2000. He had a lot of achievements and contributions to the field of computer science. He wrote several algorithms, including the SPF algorithm, the Banker's algorithm, which was an algorithm that was used for resource allocation and deadlock avoidance. He introduced the stack data structure, which is really popular in computer science and is a major topic, as well as structured programming, which he wrote the book on structured programming. He wrote the shunting yard algorithm, and he also developed the first compiler for the ALGOL 60 computer programming language, which is used for writing program is using a lot of mathematical functions. It's based on writing math functions. So the syntax follows a lot of math, and he actually wrote the first compiler for this language. He received some awards during his lifetime. In 1968, he published a paper on cooperative sequential processing. He received the ACMPODC Influential Paper Award for this paper, and they actually changed the name to Dijkstra's Prize after he won this award, which is a little bit more catchier than ACMPODC. And he also received the Turing Award for his contributions to mathematics and computer science. So the SPF algorithm is used to traverse the nodes in a network or in a tree structure. It's taught in discrete math class for tree traversals and graph theory, along with breadth first search and depth first search algorithms. Finds the lowest cost from the origin to the destination node. Each edge in the graph is weighted, so it uses weighted graphs, which is a big topic in discrete math. It's also used in networking, and the routing protocols that it uses actually are called OSPF and ISIS, and they are two major routing protocols that are even used in the Cisco routing devices on major networks today. This is a graphic representation. I don't know if it's actually visible in this video because of the lighting, but this is a graphic representation that shows from the starting point. You're actually at the origin, which is usually on the left side, and it's set to 0, its value, and then you would determine which of its neighbors have the lower weight on the edge, and you would move to that neighboring vertex based on the lowest edge, and then you process the neighbors to the new current node that you move to find the lowest edges for that vertex, and then you would go back and move to the node that is on the lowest edge, and you process the rest of the network, and you would add these vertices to a list of your nodes to as an ordered list to start the starting node to the end node or your destination node to show the shortest path, and then you add up the edge weights for each edge traversed in the tree. So you would get the total sum of the weights on each edge in the shortest path and get the total, and that will be your total weight for the shortest path. Dijkstra made many contributions to the field and received many awards and accolades, and he's known as one of the founding fathers of computer science, and even his contributions today are still significant and being taught in computer science courses around the country. So, to explain the shortest path first algorithm, I have the graph of a network drawn here, and you actually will set each node or vertex to infinity, set the origin to 0. Now you examine the neighboring vertices for the origin, and one edge has a value of 2, a weight of 2, and the other edge has a weight of 4. So you process each neighboring node and you assign the value 2 to node C here. So you would replace the infinity with 2 and replace infinity with 4 for node B. And now you would move to node C because it has the lowest weight edge in the network. And you would process the neighboring vertices for C. And if you can see here, the weight edge for C to B is 1. The edge to C to D is 8, and from C to E is 10. So we process B because it has the lowest edge. And now you replace 4 with the path from the origin to C and from C to B, which is 2 plus 1, because this first edge has 2 and the second edge has 1. So you replace the weight on node B with 3, which is the sum of 2 plus 1. Now you would examine the edge to node D and replace infinity with 8 because that's the weight from C to D. And from C to E, you would place infinity with 10 because that's the weight from C to E. Now since your lowest weight or lowest value for the neighboring vertice for C is 3, you move to vertex B and examine its neighbors, which the only neighbor it has that hasn't been processed is vertex D. So you examine the edge and the weight value from B to D, which is 5, and since the weight for vertex B is already 3, you add 3 plus 5, which is equal to the current weight already at D, so you can leave it at 8. And then you can move to node D, or terminal D, since it is the only neighbor to B. And then examine the neighbors to D, which are actually Z, the end node, which is the destination, and vertex E, which if you can see the edge weights from D to E will be 2, and from D to Z is 6. So we want to see if we can find a shorter path to the neighbor on D, which is currently at 12. Excuse me. So the weight from D to E is 2, and the current path total to vertex D is 8, so we add 8 plus 2, which is less than the current value of vertex E, which is at 12 right now. So we replace 12 with 10, which is smaller than 12. And also we want to replace the value for Z, which is our destination, with 8 plus 6, which will give us 14. So we replace infinity with 14 on the end vertex Z. And now we want to examine the neighbor to D, which is E. We move to this vertex and As you can see, the edge from E to Z, the destination is 3, and the current weight on destination Z is 14. So if we add the current weight of E plus 3, which will give us 13, is less than the current path to the destination Z. So we have the path from vertex D to E, and then from E to Z, which is our destination, which will give us the total cost of 13, which is the shortest path of traversing this network from the origin vertex A to the destination vertex Z, which is the underlying concept of the shortest path algorithm.